So now we're gonna, after we covered these two beautiful properties, network invariance and equivariance, at least we define them and we understand what they mean and what they stipulate in the network and the input or intermediate layers of the network. Now we're going to explore together convolutional neural networks for one-dimensional inputs, okay? So we're going to look at one-dimensional inputs over here. And so in this example, as I mentioned, so in this simple example, we will see that we're starting off with a reductionist hypothesis, which we will challenge and change towards the end of this section. So our hypothesis is that all pixels share only one universal mapping, producing new local representations. So one universal mapping here means that all pixels actually have only one single W to learn. And this is, the kind of universal, this is the hypothesis mapping of our data that we want to learn. Okay, so let's hypothesize that we have an input data X. It has I entries, so we have I elements here, and this is our mapping function. It's a three-dimensional mapping function. So this is the kernel that we're going to use. It's a one-dimensional here, and 1 by 3. I mean, like it's 3 by 1. So W actually W belongs to our 3 by 1. Okay, of course, transpose is 1 by 3. And then what we want to do is to perform a convolution. So convolution is a very simple operation. So here in this example, mathematically, how do we actually write it? We write it in this way. So we apply, basically, we multiply all of these, we take the input and we apply W to a three-dimensional input. So we have three neighbors, so xi minus 1, xi, and xi plus 1, and we apply our filters or our kernel to these three inputs. So here, this is the convolution operation, and we can express it mathematically like this, okay? So we vary the j here, and j is the index of actually the index of the input, one of these three neighbors. So it's actually a very simple operation that gives us the final transformed input data by W. So what is the input data here? So we have x1, for example, x2. So let's write it maybe in terms of xi minus 1, okay, xi, and xi plus 1. And we have our nice kernels. So W1, W2, oops, and let's do a nice circle, W3. And then we perform this kind of, element-wise multiplication, and then a summation, right? And this will gives us the final output, which is our Z. So Zi for this pixel, centered at xi. So what did we actually do here? We first took three values, we reduced them into one. And this one value, if you think about it in terms of images, this in terms of patches, for example, it actually reduced this whole like kind of these three values. If we have three values here, let's take them maybe inside for ease. It reduced these three values to a single value over there, right? So somehow it's collapsing information, it's reducing information by learning how to represent it in a lower dimensional space in a better way. So hopefully this Z will be a better representation of what a cat is. This Z will enable us to distinguish between an image that has a cat or not. So these learned representations, they will tell us about the patterns inside the data, okay? Cool, so that's it. So it's a weighted sum of, you know, like of the original pixels multiplied by this or guided by this kernel. Now let's look at this nice, you know, example right here. So we have multiple examples, and if you think about the first example, A. So let's focus on the A. So I want you guys to look at this part, okay? So in the first part here, what we have a one-dimensional convolution with a kernel of size 3 by 1. So this is our kernel. And as we start off, if we start off from the beginning, what do you guys know this? We start from x1 to x3, so we have 6 inputs here. And we do our convolution, we get z2, z3, 4, and 5. So with this kind of sort of convolution, what happens is that every time we shift this this kernel by one stride, one step, we're going to get a value. So we get z3 here, z4, etc. So here, for example, we got z3. All right. So, but what you guys notice is that actually these two values are missing. So there are two values that we cannot calculate if we start from only x1. The z1 is not produced, and the z6, because actually these are, you know, like here, the kernel starts from the first position, and when it starts from the first position, it only produces z2. So how can we produce z1? We need to actually go outside the image or outside the data. So we need to place our kernel over there. And if we do that, actually, we can calculate z1, and we do the same. We can calculate z6 by adding what we call a padding, okay? So here, what is a padding? A padding is adding a 0 here to get, you know, the z1. So this channel is not actually very important because here, this weight will get nullified, but you can think about it as summing only these two weights, actually, right? So that's how you produce a z1. If you think about it mathematically, all that counts is this part of the kernel. The top part is zeroed by the 0 padding that we added, which is a 0 on top, as if we have an external, you know, member over there. Okay, so an imaginary pixel that's not existing that we have added, and this is, you know, 0 on top. We do the same in the bottom. We add a 0 over there, and here the z6 is actually generated by only w1 and w2. So w3 here doesn't count, and the last pixel doesn't count. So you can only sum w1x5 plus w2x6. All right. So the 0 padding actually allows us to kind of, you know, it's a very nice idea because if you do not do 0 padding, what happens? If you remove the 0 padding, you're going to end up reducing the dimensionality of your consequent or follow-up layers. So every time I do convolution, this will decrease. I cannot maintain the same dimensionality, which is 6 elements, okay? So this will lead to a consecutive or progressive reduction of your input and may not turn out to be well. So you actually need to kind of, at some point, you need to kind of either maintain the same dimension or sometimes increase the dimension. So we'll see that later. So here, as I mentioned, we do the 0 padding for that to avoid that. And let's look at this example. So we're going to do it again. So here, in this example, which I was talking about, is when we don't do the 0 padding. So without padding, there is no padding here. So if we don't do any padding, sorry guys, so no padding, this is what we call a valid convolution, okay? So a valid convolution, it means that, you know, like the kernel fits within the input range, and it reduces the size of the input. So the representation will always decrease in size, and this is something maybe not that good to have, but you guys can notice that right here, we're gonna end up with only 4 values because we didn't do padding. And if we repeat that again, if we do 1 and then stride of 1, we're gonna end up with how many values here? Only 2 values over there, which is, you know, Z5 and Z6. So if we apply the 3-dimensional kernel to our the first layer right here that we produced, we will end up with the size of 2 for the coming layer. And so this is not really good because every time we're collapsing the network in size, and it will be maybe difficult to adjust it to the final number of classes if we have maybe 1,000 classes over here, right? How are you going to make the network produce something that has 1,000 values or probabilities at the end? Okay, so yeah, so that's that. So this is it's good to know that when we pad, we call it just convolution, but when we do not pad, we call it a valid convolution because we're not adding some imaginary values or imaginary zeros here. All right, now let's move forward, and we're going to cover now this part, which is basically different examples of a network using different strides, dilations, and different kernel sizes. So remember, we talked about the family that we have right here of convolution operations, and we had 4 variable size, padding size, stride size, and dilation rate. And in this example, we're going to look at the formula. So what is the mathematical formula that allows us to calculate the size of the output channel? So let's start with the first example. So in this first example, what we have first one padding, okay? So, and then we do a stride of 2. The dilation rate is 0. So a stride of 2, let's copy this, guys. Okay, so we're gonna copy this. And then I'm gonna show you a stride of 2. So a stride of 2, it means first we will take the first input, right? So we'll do the convolution. And then instead of taking a stride of 1, we're gonna take a stride of 2. So we'll find Z2 over here. And then another stride of 2. And then another stride of 2. And we'll get our beautiful outputs here, 4 different outputs of the input image. Okay, so these are our outputs. And then when you have a stride of 2, what happens is that you're collapsing faster your network. So even with the padding, you went from 6 to only 4. So the striding here, when you have a stride of 2, it allows you to look at all data, by the way. So you're looking at all data, including, of course, the padding here, but you're reducing the dimension quite fast. Okay. So now let's look at the second one, the second example. So we have stride 2 and size 3. So this is the same example. So we just moved it, shifted, and we showed how we produce this. So now for C right here, so we have 3 padding. So we need to have 3 padding because the kernel has a size of 5. So to cover the guys on top, right? So we need actually to add 3 zeros on top. So if you guys, actually I'm not, maybe I can draw this quickly. And let's see what happens. So here we do the convolution, and then we do the summation over there, and we do the summation. Let's move this. So to get the first, the first actually element, we need to actually add the padding. So here, right? So that's actually, we need to add a padding of 2, I think, right here. So because of padding of 2, we already cover that. And if we do this, yeah, so we need a padding of 2. So in this example, it's good that I verified it. So here, actually, it is a padding of 2. They didn't mention it, but you can see it from the example. We don't need 1 more 0. So if we do 2 padding over there, and we have size 5, the stride is 1. And dilation is 0, so we don't dilate. So basically we start from this one and we go over all these guys until we get the final, basically the final output. So that's quite simple. Now, what happens when we dilate? Okay, so here, this is an example where we do dilation. And the dilation, it means the kernel that was 3 by 3 originally becomes, dilated by 1, all right? So here somehow what we have missed 2 values. So if we have a dilation of 1, then in this example, the kernel size has become 1, 2, 3, 4, 5. So it's 3 plus, 2 times the dilation, if we call it D. All right. So D is equal to 1. So here we have a 5 by 5 kind of kernel, right? So we have 5 by 5, but you don't see it. So here, these guys are actually zeros. So we added 2 guys over there that we don't care about, okay? So what happens in this dilation? You can see that now with this example, how many paddings do we need? So let's draw this and shift this along the input one-dimensional data. And here we go. So if we're going to shift it, so starting with the first one right here, we actually need to also add 2 other values. To get this value right here, we need to do 2 paddings, and you move along like this. Okay, stride is 1, so it's fine. So you can get all these values. So you can see, because I'm striding by 1, if I stride by 2, you will skip more numbers and you'll have, you know, smaller output, not the same size. All right, so here also we have a 2 padding. All right, cool. Now, what is the formula that we are using right here? So the formula is actually simple. How do we, so the question here is that we have the size of the input channel. So let's call this the size of the input channel. This is my input channel right now, like at a particular layer. And then this is my output channel. And what I want to know the size of the output channel giving these variables, the size, the stride, the padding, if I have padding, and we're going to add dilation at the end. So the formula right here is written. So I've written it for you. You guys can try to derive it yourselves and spend some time to kind of figure it out or remember it. It would be a good exercise to kind of sit down, do this manually, and try to derive this formula, you know, by hand. So this formula is actually quite simple. So let me just use this example. So we have P denotes the number of padding, F the kernel size, N the input size, the size of the input channel, and S is the stride. And the output size will be actually N plus 2P. So N plus 2P is the size of the image. So because if you have an image and you had it a P right here, so it's the padding of 1, you need to add another P over there. So the size of the image has changed from N to N plus 2P. Okay, so times N plus 2P. So this is the size of my my image, if it's an image, or my input. So we added 2P here. So if we add 0 on top, you need to add 0 in the bottom. So that's why we have a 2P over there. Okay, so this is the size, the total size of the input channel with the padding, and then you remove the size of the kernel, which is 3 right here, and you divide it by the stride. So that's why the stride here is a downsampling. It's a downsampling kind of operation, because as the stride increases, the output size will decrease. Okay, so, and then you add a +1 to this formula. And if you don't have an integer, you take the lower bound. So let's say if you have 2.5, you will take 2 here. So this is, you know, the lower bound kind of value of the quantity inside of it. So so that's that. So this is the formula. Now, if we do have, if we do have dilations, what happens when we dilate? So if we dilate, which element we need to change is actually the F. So let's think about it in a bit. But what I want you to do right now, guys, is to take some, you know, like just a minute and try to calculate the size of the output for this one. So take some time and let's calculate it. So we have P is equal to, in this case, so P is equal to 1. S2, the dilation, we don't have dilation, so it's good. So you guys can try to find this number 4 over here. So let's take a second and figure this out. So the solution, as you guys can see, is very simple. So first we take the number of inputs. So we have 8 plus 2 times the padding, so plus 2. And then you do -3, and you divide by the number of strides, 2, and then +1. So here you need to take the lower bound. So This gives you 7 divided by 2, so that's 3.5. The lower bound is 3, and then plus 1, that gives you a 4, and that's why we have a 4 hidden units in the output channel, okay? Cool, so that's that. You can apply this to all these examples, and if we have dilation, actually, you guys need to change the size of the kernel. So here, if we have the dilation, you always add, so you replace F with F plus 2D, because you're adding, you know, twice the dilation rate, and you can actually calculate the output. But you always need to think about the padding, so don't forget, guys, about the padding, because we're adding the zeros over there. So you need to kind of make sure that these are added properly. So I'm going to use the same color because I added them in red. And here we go. And you can check the formula once again, okay? Cool, so now you know how to design your network, because this formula is actually very powerful. This allows you to set the number of outputs in the next layer, and if you want to move to the next one, you can design your strides and dilations and sizes based on the size of the input, and basically get the output size that you want. So try to kind of get what you want at each layer until you converge to the very last layer where you have the target output size, which is, I don't know, number of classes, or it's an image, it's an n by n image if you're doing, for example, image segmentation or object detection with segmentation. So you will have multiple outputs. So there are different things that you can have as outputs, and you need to design your neural network in such a way that it can accommodate that, okay? So now we're talking about, so we talked about strides. We're going to talk about convolutional layers. So convolutional layers are actually very simple. So we have already seen that. So here in this example, every single hidden unit in the output channel is calculated as follows. So first, we need to do the convolution. So this is the weighted sum using the convolutional kernel. And here we have, we're still in the one-dimensional case. So this is one-dimensional input. So it's very simple. All right. And then we add the bias. So we need to add the bias after we do the weighted summation here using the convolution. Okay, weighted sum. Add the bias, and then apply the activation. And this is how we get the actual value at HI. So if you guys remember, this element right here, we called it ZI. So basically HI is equal to the activation applied to beta plus ZI. All right, so a beta is our bias, and it's another parameter that we need to learn here. And it's like, you know, we fix it also throughout the whole network. So the network has in this layer W1, W2, W3, and it also has the beta. So these are the 4 elements that we need to learn in this, you know, at this stage, okay? So it's so simple to write. And what I want to discuss or show you now is something really exciting. And I think this is something really interesting, okay? It's these 3 matrices. So colors here indicate the same value, all right, in these matrices. So what are these matrices and what do they represent? So first, in A and B, so A, we have the network and its corresponding mapping. All right, here, matrix, and then this one, and that one. All right, so these are in correspondence, but we start with an FCN and we move towards a convolutional neural network, and you can see what happens to the matrix right here. So somehow this matrix compared to a fully connected network, so let's put this matrix right here. So this matrix becomes sparser, right? So the matrix has so many values. These values are all zeros. They disappear. These connections completely disappear. Okay, and then when you, so this is the first transformation that we see from A to C. Okay, so let's look at that before we go into the third case. So the first 2 cases. So first, we have here an FCN. So if we have, for example, D elements here, and we have D outputs. So we're going to have a D by D matrix. So it's a D squared matrix plus, d biases. So these are d squared, basically, weights. And we have d biases. So this is the size of our network, okay? So if you have, for example, thousands or millions of input pixels, with a stride, with a fully connected network, you're going to end up with a really huge number of parameters. Why is that? Because your matrix right here has a lot of values, different values to learn, and it's a huge matrix. Okay, so if you have, for example, an image 256 times 256, you need to calculate this, and this becomes, your basically d, right? And then you need to square it. And these are the number of parameters plus d biases, and that's a lot of weights to learn in a single layer. This is just a single layer. We haven't even made the network deeper yet, okay? So now, if we move to convolutional neural networks, what happens with convolutional neural networks? So let's see, this is our convolutional neural network. It means we have exactly the same weights applied to three neighbors. So x1, x2, x3 have these three weights. Then x2, x3, x4, we apply exactly the same, weights. So the colors are the same, okay? And then for the ones on top, for h1, we have a zero padding on top. And for the h6, we have a zero padding below. All right. So then what happens here is that actually you can think about it. So we're kind of taking this matrix, but we're translating, we're taking this kind of these diagonal elements, and we're shifting. And this is exactly the shape of a matrix of a convolutional neural network. And here we have a beautiful CNN matrix that models the weights between the input x1 and h1, etc., between input channels and output channels. So this is, if we write it down in a better way, so this is the input channel units, and these are output channel units or output units, okay? So somehow we made the problem simpler, sparser. We have exactly the same numbers that appear over and over again, and these numbers are these guys, basically, okay? So it's the same thing that repeats itself. So easy to learn. And actually, you can collapse this matrix if you want into these only three values. As opposed, so this can be further reduced to only these three values, okay? Because they are repetitive, duplicate. So that's it. It's okay, so not duplicate. Let's do paste image. It's pasting something else. So, okay, sorry guys. So let's do copy, paste image. So basically this whole network is reduced to only these three values, and that I cannot, can I rotate here? Yeah, so I'm having problems, but it's fine. So you guys get the idea. So basically everything is reduced to only these three values over there. All right. So now the problem that was d squared now is reduced to only 3, which is amazing. Okay, it's the size of the kernel right here. And then if we want to reduce it even further, right, we can use a convolution with a stride of 2. So if we have convolution stride of 2, so we have the first convolution, then we skip 1, 2. We have the second output, 1, 2, and we have the third output. And in this case, we get this matrix, and it's even a smaller matrix because we have reduced the size of the output channel. So we have only 3 values over here, and the size of the input is the same, okay? So if we want to save this matrix somehow, you guys can see that, we have reduced the size of the network and the size of the matrix. But at the same time, if you think about it, what I am storing towards the end is, these kind of these 3 values. And of course, you need to, have these, you need to store the values inside the H1, H2, H3, etc. So all these need to be stored properly, right? That's why we have the size of these matrices. But these matrices can also shrink as we increase the stride of the convolution. And we can also make the relationship or the mapping here between the input and the output sparser as we set many zeros over there through this convolution neural network. So this is a very nice example that shows us the differences between number one, FCN versus CNN. And then using a CNN convolution neural network, one-dimensional with a stride of 1, and when increasing the stride, and what happens to the parameters or the weights that we're learning and their dimensionality. All right, so we covered strides, formula, convolutional layers, how we actually calculate the hidden layer value HI, and you can code this up. It's easy to code up. And now we're going to talk about channels, okay? So as you guys remember, in the first section of this lecture, we covered channels right here. So we motivated channels and how we got the idea of, getting or defining multiple kernels and why we need to define multiple kernels. And this was the idea that stimulated, the concept of channels or adding channels to convolution neural networks. So here, let's see how these guys actually operate. So in this example, I'm going to, so in this example we have, so I'm gonna take this guy right here, just seal it and put it over there. All right, and now we go back to our nice figure. So here we have basically, we store the input H2, so that's the output of the first convolution, and plus you add the bias and the activation. That's why we have the activation right here. It means we have added the bias, okay, so there is a plus beta somewhere, and we applied the activation A. So you applied the activation A over there. Now, when we take this network, we do the same. So we can, if we do, like padding, so one padding, you can see that we can get these values the same as before. But what happens is that now we're going to apply a second kernel. And when you apply a second kernel, this is our second kernel right here. So I'm going to actually remove this inside and this color it differently. So our second kernel is blue, right? And we take the second kernel and we apply it to the network. So every time we apply it to the network, we're not gonna get a value. Let me remove this. So the value that we're gonna get is actually over there. So it's like this. So applying a second kernel will get us all these values, right? And the second channel, so H1, H8, 9, 10, etc., 11 until 12, and with, of course, the zero padding. And this is, our second kernel, kernel 2, that will lead us to the output elements in channel 2. Okay, so this is, channel 2, and this one is, I'm gonna put it, channel 1. Okay. So it's actually very easy, and you keep on stacking that over and over again. So you can add more, actually you can add more kernels, you can add many channels, as many as you want, because they are calculated, independently. So you can, if I copy and if I can paste image, so we can add other guys here, and you keep on adding, until you get many, many channels with different kernels that you're trying to learn. Of course, these are learnable, and this is what we're aiming to optimize, okay? So we're trying to learn this W of kernel 2 right here. So what is the W? So now, how do we actually then concatenate this? So it's actually very simple. So once basically, when you do the convolution at a next layer, so now the next layer has multiple channels. So the input here, we have 2 channels. So if you guys remember, here we have one. And for this input, we have actually 2. So for these 2, it's very simple. So we apply basically these 2 kernels. So we apply the first kernel and the second one. So let's choose a different color. So we apply basically, like the first layer will go through the first kernel. Okay. Like this. And then the second channel will go through the second kernel. These guys, and you can see the arrows, right? So you can convolve with these guys. And then towards the end, we will just do a summation. So we will sum all of these, and then we're going to get a single value in the output channel. Okay. So basically, it's very simple. You do the multiplication and then you sum. And here, you're summing across channels. So this is basically sum across channels outputs, and you'll get the value over there. So as I mentioned, it's like this operation that we talked about earlier. So as if you're not, at the end, you're taking all these, kernels, you're applying them, and then you're summing the representations and collapsing them into a single value over here. So this is, how you do it when you have many channels. And now let's look at an example together. So we're going to cover 2 points, a hands-on example, and then receptive fields, and we'll take a short break. So, all right. So this is an example where we have, it's a simple example. We have a 28 by 28 input image. So this is the size of the image right here. Okay. And then first we apply a kernel of size 3 by 3. And then we apply pooling by 2 by 2. So what is pooling? So I know we haven't covered that in detail, but pooling is actually, if you take, for example, a 2, like if you have a pooling of 2, you will divide you take a kernel of size 2 by 2, and you'll reduce it to a single value. Okay, so if the size here is 2, you're going to basically divide it by 2, and then you're going to get one single value over there. So pooling, for example, we'll see different examples of pooling. So for example, we have what we call max pooling, and 2 by 2 means we take 2 by 2 here. It's a 2D image. So this example is for a 2-dimensional image. So we went from 1D to 2D. And in this simple example right here, in the pooling, we have, for example, let's say we have 1, 2, 3, 4. If you take the maximum value, it's 4. So you're only taking a value of 4 over there. Okay, so pooling actually reduces the dimension. It decreases the dimension, and you divide by the size of the pooling. Okay, dimension of the input channel. And next we apply another kernel, another pooling, and we do flattening. And here the number of channels are actually predefined. So you say, I'm going to learn 32 kernels. These are my 32 kernels. In the next layer, I'm going to learn also 32 kernels. In the next layer, I'm going to make more kernels. So I'm going to learn 64 kernels, okay? But they're at lower dimensions. And here I'm going to learn also 64 kernels at lower dimensions. All right. So these are actually 32 is the number of channels or kernels. And it's this dimension right here. Okay. So now what I would like you to find out is the size of the output. What is the size of this output? So the output, so we have 32 channels. So 32 times what exactly? So you need to identify the size of these, squares by applying the formula. And the formula, if we take, it's actually the input size. If you do padding, we don't have padding here, but it's 2p plus 2p. You add the padding minus the kernel size divided by the stride plus 1, and you take the lower bound. So this is, the output size. So I would like you to take, a few minutes and try to calculate this, and we'll be back in a minute. So it's quite easy to actually calculate the size of these channels. Like, for example, the first one. So we have 32, and it's times what is the size of this, output, basically, image. So here what we have we have n equals 28, so that's the input data, plus 0, so no padding, minus f is 3 divided by 1 stride, and here, you know, plus 1, and this simply gives us 26, so this is actually 32, you know, times 26 by 26, okay? Now, because we're doing pooling, so pooling means we divide by 2, so we have actually here a, you know, 26 divided by 2, so that should be 13 by 13, and we have 32 channels, okay? Times 13 by 13. So this is the dimension of this whole tensor over there, okay? Now we do a kernel of 3, so let's calculate again. So the input size is 13, and then minus 3, that's 10 divided by 2, okay, and plus 1. So 13, so 10 divided by 2, that's a 5. So here we should have something like, so if we have 3 by 3, so it should actually be 5 plus 1. So we have 6 by 6. Am I right, guys? Are you following?
Yes,
So
Dr.
13.
Yeah, with you.
Okay. Okay, good. And then we have here 64. And then if we do padding by 2, so padding by 2, it means 6 divided by 2. So we're going to end up having 64 times here, it's 3 by 3. And then if we flatten it, if we flatten all of this, we sum over the number of channels. So we collapse along this dimension. We're going to end up, if we sum over the number of channels, we're going to end up with a matrix of size 3 by 3. And if we flatten it, it means we vectorize the matrix. So we're going to have 9 values. Okay, so if we have 9 values over there, then it means what exactly, guys? The final layer, the class probability, we have 9 values. It means we have 9 classes. Okay, so we designed this network in a way that we want to get 9 classes at the very end. All right, cool. So now we're going to look at the next stop, which is receptive fields, and it's a very interesting concept in deep learning in general. Okay, so we want to measure the receptive field of each neural network, and in a convolutional neural network in particular, the size of the receptive field actually defines the region in the input that feeds into a particular node. So for example, if we want to calculate the receptive field, the size of the receptive field of this particular node right here, okay, so 3 is actually the number of, it's the kernel size over there. So we have basically 3 things here. Let me define them first. So we have the kernel size, we have the size of the output channel, and we have the size of the input channel. So for example, here, the size of the input channel is 3. So we have 3 elements. So let me take, so we have 3, and then, sorry, so we have 1, the size of the input, we have only 1. So 3 elements is actually what we're looking at with the kernel. We have only 1 channel, so that's a 1. And then we have the output channel. We have 3 outputs. Okay, so that's our 3. And then we have the size of the kernel. Actually, the size of the kernel looks at 3 elements, so we have a 3 over there. Okay, so that's 1 times 3, 1 by 3 by 3. So that's our omega that we want to learn here, our mapping function that has all the weights. And when we say that the receptive field of a particular node is actually the input, the region in the early input that feeds into it, basically, if you want to know the receptive field of these nodes, it's actually this area. So this area right here in the original input, it allows us to control the values right here. So it impacts or influences the values inside these nodes in this layer. So if you look at, for example, this node, this is the receptive field composed of these three values of this node. So this node has a three, dimensional receptive field, which means it can look at only 3 pixels in the original signal or in the original input, or 3 inputs, okay? 3 units here. So you can see that all of these actually, all of these nodes in the second hidden and the first hidden layer, H1, they have a visibility or receptive field of size 3. All right, so that's a 1. Now, if we do here, if we look at B, the second example, so what do we have in B? So we added another hidden layer. So we have, let's use a different here. Okay, so we have a second hidden layer. And in this second hidden layer, we're applying an omega, a mapping, a tensor mapping of this size. So this is 3 is the size of the number of channels in the input layer. 4 is the number of channels in the output layer that we fixed, of course. So this is a target value that we fix. And then we have the size of the kernel, and the size of the kernel here is 3. So what do you guys notice? That now with this kind of, convolution neural network, if we look also at the first, going from the layer 2 to a layer 1, okay, so looking at this, we have a visibility of 3, okay, so the field, each node here looks only at 3 nodes in the previous layer. But if we take a node, okay, and in this, like in this, like in the view field of these 3, right? So here, this is the view field of this particular node. So let me show it right here. So maybe it's better to draw it. So this is our node right here. So this is the node, and this is its view field. Okay, so it can view all these pixels. Now, if we want to trace back to the original input, if we trace back, now we need to look at the view field of each of these nodes, right? And if you look here, the view field of each of these nodes now has extended. So we have a view of how many nodes? 1, 2, 3, 4, 5, 5. So what do you guys notice? The difference between A and B is that we have increased the number of layers. And as we increase the number of layers, what happens is that our receptive view increased. Okay, so this is something that is nice about increasing the depth. So increasing the depth of the network, okay, leads to increasing its receptive field. Okay, so especially in this particular design where you kind of have the same number of nodes in the output. Okay, so now let's look at C, the example C right here. So in this example C, we have changed something. So before we used a stride of 1, now we are using a stride of 2. So stride of 2 means that, okay, so we have our network. We're taking, for example, the first activation. So what happens in this, when we're striding here, when we're taking the stride, we're not looking at, how do I say, like we're skipping one connection. Okay, so we're moving by 2, not by 1. So in this case, in this example, we have a view of 3 by 3, so that's fine. So here it's a, this is the example we had before. So all of these view actually this part. And then when we take, like these, now the elements in the hidden layer 2, and we do the, the striding of 1 is good here. Also, the striding is okay. But what happens over there? So here, when we say a stride of 2 kernel 3, it means that we actually have, we have a lower number of channels. We decrease the number from Let me think about it just a second, guys. So in this example, if we think about the striding, right? So we're doing a stride of 2. So first we're going to look at this, and then we're going to look at, so in this example, we're going to look at the first 3 and then stride again. So by 2, so we will end up having only a smaller number of pixels, okay? So however, this what leads us later, because if you look at this, it won't match up. So if we do this right here, we're gonna have only these guys, right? So these 3 guys over there. But because of the striding, we have kind of shifted this a little bit up, and we will end up having completely different view because of the striding. So we'll end up having a larger view. So the conclusion here is that when we increase also the stride, so we increase the stride as a, you increase the stride, okay? Then the field view, or the receptive field, also increases. And this is what happens here. So we went from a 5 up to 7, okay? Now, so in this case, right? So here, as I mentioned, so the first channel takes a 3, and then you move by 2, so you move down. So yeah, so now we can see it actually clearly. So if you take this first input, it oversees these 3 guys, right? So these 3 guys, and you have all these guys, and then you need to skip 2. So as you skip 2, what happens? You're gonna, like start from here as you skip 1 and 2. So it starts from there. So this block actually now is responsible for these units over here, okay? Because we're striding by 2 when we are doing the convolution, and you're gonna do it over and over again. So if you want to see, for example, this input, so let's choose a different color. So different color. Let's use this, for example, okay? So for this one, you need to even stride by another 2. So you're going to do 1, 2, and it's, so you skip 1, and you skip another one. So this will be the field view of this guy, okay? So you guys can see how striding actually operates on the input channel, and how we're getting different actually receptive views over there. So so in the last one, right here is actually the same rules. So we apply them. So we have the striding of 2 over here, okay? So the rest is good, but this striding happens over there. And then when you do stride, you guys can see that now if we make the network even deeper, so we added another H4 layer. So here we were at 3, so we added another layer, and this part of the network, this output channel in the 4th layer has a field view of the whole image, which means if you trace it back, you can see exactly the full image. So this, these numbers actually are impacted or are determined by the full image. And this tells us a lot of things. This tells us that basically when you reach the last layers, what happens to the learned representations, the learned feature maps, the output convolutional maps. The output convolutional maps, they will capture more global information, okay? The early layers, they capture more kind of detailed information. And you can see it here. The early layers, they capture detailed information. But, like, especially even if you have, oops, froze. Do this. Yeah, so the early layers capture more local information, and the late layers capture global information because you can see the whole image if we have, of course, deeper networks, okay? So this is more local information. So this is why when you display your feature maps, your H1, so when you display your learned, when you visualize these feature maps, you will see tiny details. Like, for example, these images are able to capture edges. They're able to capture, for example, like some contrast, right? So these are kind of, very simple properties or patterns that they are capturing at a very local level. So if you have a cat, it will capture, this edge, or this kind of edge over here. So these kind of small, like patches that we output, they will be able to capture local information. And the ones at the very bottom, they will capture the whole kind of picture, the whole pattern of the image that allows us to identify that it's a cat or not, okay? So here it's, you can view this through this network, and here you can see that we have actually all these values in the receptive field. As we design this network in this way with a stride of 2, when moving from layer H2 to H3, using this kind of convolution, and as making it deeper, it increases the receptive field. So these are the take-home messages from this example. And now you guys can also play with this. So this is another example. So I'm going to just remove that. So you can take also a few minutes to play with this network. So what we have here, we have an input with 40 values. We apply a convolution of stride, size 3, stride 2, and the output channels, the number of output channels is actually 15. And what we want, we have also a beta. So this is the omega that has all the W values, and we need to learn 15 biases for each channel. Okay, so each channel has a bias and a particular kernel to learn. So 15 kernels to learn, and this is the size of the output. So the exercise here is to identify this, like the size of the output. So what is the size of each output channel, and then the size of the final output. Okay, so let's take a minute, and I want you guys to calculate this quickly, and then I'll show you the results. All right. So here's solution. So basically, first for the size of the first output channel, H1. So we take the number of inputs. So we have 40 minus the size of the kernel, which is 3, divided by the stride, which is 2. And you add a +1. So this gives us basically 19 here. So the first answer is 19. And if we apply this rule over and over again, we're going to get 9. And then the third layer will be 4 by 15. And you can see the shrinking. Now the last one is 10. So this is, basically the fully connected layer. And in the fully connected layer, we apply this operation over here. And we just, vectorize this one. And what we get 10 values over there. So these 10 values, we turn them into probabilities by applying a softmax. So as you apply the softmax, you get the probability of the classes. And these probabilities, for example, 0.8, 0.01, 0.2. So the value, the element, the class with the highest probability would be, identified as the target class. And this is, for example, in this example, if all these values are low, then we're going to pick class 1, and class 1 will be the answer here. Okay, cool. So now this is a very interesting example or a very interesting experiment actually on MedMNIST dataset, on MNIST dataset, the MNIST dataset. There's also MedMNIST. So on the MNIST dataset. And this compares basically two kind of approaches. So in the first, let's think about this. What do you guys know this first? So in the first, let's figure this out. So one of them is an FCN, fully connected network, and the other one is a CNN. So let's identify which graph or which plot corresponds to the FCN and which one corresponds to the CNN. So the first one, here we have the number of training steps, okay? So we're training our algorithm. We have a large number of training steps or iterations, and this is the error or the loss that we wanted to decrease. Now, if we look at the train set first, the first train set here decreases faster, right? So we see a fast decrease over there. So it kind of, reaches the optimum faster and then continues to decrease and it's more stable. As for the test set, okay, so for the test set, we see that for this example, what do you guys notice? So this is actually a lower error. Okay, so we have a lower error here, and this error over there for the testing is quite high. So in this example, actually, if you think about it, if you're doing convolutional neural networks and you want to kind of learn a model that enables you to capture locality in images. So this is an MNIST. The MNIST data is a vision data of digits. So we're classifying handwritten digits, like for example, 2, 1, etc., 3. So in this example, which one you guys think is an FCN and why? So the one that generalizes actually better, the one that has the lowest error, right, is the one that turns out to be the, like the CNN here, and this one is actually the FCN. And what this tells us, it tells us that convolutional neural networks are more generalizable, as maybe they can capture better patterns that are, invariant, that have some, nice properties across all this data set. So we're able to capture what identifies a particular digit. So in this example right here, this tells us that CNNs, they are powerful at learning. CNNs are better at learning good image or data representations that generalize better, okay? To unseen data. Okay, cool. So this was just, a simple example. And what I would like you to do, guys, now is, if you're just watching this video, I would like you to fill in this, what we call a recall box. So try to remember all the rules and the principles and everything that we have seen from the very beginning in the past, I think few hours. So write down every single thing that you remember about, FCN, how we moved from FCN to CNN and why, explain the formula, for example, of a convolution, the output, the formula of a convolution first. What is a convolution? What are the properties of a convolution? So in this exercise, basically, you will try to remember all the important points that we discussed, and maybe you can have some universal principles, and these universal principles, I misspelled, so principles, okay? So in these universal principles, you'll write, for example, the rule of, learning independently and having these individualistic networks, right? What kind of rule you can derive, the equivariance, the invariance, all these are important principles, and equivariance also. I'm gonna just write the equi here, okay? So you guys get my point. So basically in this purple box, it's a retrieval task, and it's a very important task because eventually you're attending a lecture or you're watching a video, and at the end you feel that, okay, what did I actually remember from this lecture? And taking a pause after the lecture just to kind of see what you recall is actually, that's the knowledge that you retain. And this is a short memory recall task. So a long-term memory recall task would be a task where you take after a few days, let's say maybe from watching the lecture, and then you sit down and you try to remember what the lecture was about. And the more you recall, it means the more you understand and the more you have thought this through. So it's important to kind of engage with the content and not passively watch through it, because in that way you won't remember a lot, and with time it will vanish into thin